Well, thank you so much. I'm so excited to be sharing the stage with all of you. I'm going to be talking about drug repurposing for amoebic encephalitis, and I've subtitled it From Bench to Bedside to Public Health for reasons that will hopefully become clear. Um, I have no disclosures and no conflicts of interest. So my story starts with a patient. I did not set out to repurpose drugs. I was a trainee in 2021, and a patient came to my hospital, a man in his 5th decade who'd had a seizure. His MRI showed inflammatory lesions. The gray here is normal tissue, and the white is areas of is edema surrounding an area of infection. He had a brain biopsy, and it showed these unusual cells shown here, which are sort of these large cells consistent with amoebic encephalitis. A PCR was sent, and it was positive for Balamuthia mandrillaris. Now, you may be asking, as I did at the time, what is Balamuthia? I did not know this disease. I had not heard of this pathogen. Balamuthia mandrillaris is an amoebic pathogen. It was described first in 1990. It's a free-living amoeba, so it's a eukaryote. It's more closely related to humans than to bacteria. It has a tough dormant cyst stage, which is sort of a ball form that it can retreat into under harsh conditions or when faced with drugs. And it also has a motile trophozoite, which is the thing that is active and that consumes things, including brain tissue. A word on its epidemiology. Most cases are reported from the United States, South American nations, and also China. In the United States, it's mostly in California, Arizona, and Texas. The numbers are in the few hundreds. There's a slight male predominance, and it affects individuals across the age spectrum from little babies to people in their 90s. It's thought that we get it from soil. So most patients have some sort of soil exposure. But if you think about how many of us go hiking or gardening, there must be more to it than that. There's a thought that maybe we're exposed to it all the time. Some antibody studies have been very high in healthy controls. So if you think about your next sort of gardening adventure, your next hike, you might think there's Balamuthia out there. It can rarely be transferred by transplant. There have been 3 case clusters where a patient has died and then their transplanted organs have been transplanted into recipients and recipients have become ill. But what I really want to stress is kind of the really dismal survival rate of this infection. This is a 90% mortality disease. That is worse than any infection, with the exception of symptomatic rabies. Now, Balamuthia is one of 3 free-living amoeba. The other 2 are Naegleria fowlerii and Acanthamoeba. Of those 3, Naegleria is usually the one people have heard of, if they've heard of any of them. It's found in warm lakes, and the typical way people get it is diving into water and having water forced up the nose. It causes this very, very fulminant, usually there's unfortunately death within hours or days, and typically in young patients. Acanthamoeba causes what's called granulous amoebic encephalitis, or GAE, which is these slow-growing brain lesions similar to Balamuthia. Can also cause a very nasty keratitis in people who wear contacts. And finally, there's Balamuthia. All 3 are rare, and all 3 are exceptionally deadly. So I had this patient. I knew what to do. I went to the literature, and I looked at what is used to treat patients. Now, because this is so deadly, patients have been treated with a number of different drugs based on what clinicians often thought they had at the time. And the recommended treatment for Balamuthia is based only on case studies of survivors. It, until recently, was not based on in vitro data or case series. So the prior treatment to this year, more on that later, included miltepacine, azithromycin or clarithromycin, sulfadiazine, pentamidine, fluconazole, and flucytosine. That's 2 antiparasitics, 2 antibacterials, and 2 antifungals. It is not the most obvious regimen, and it's also really toxic. So the guidance was to start them all and keep your patient on them for as long as you can until you run into toxicities that you cannot control. This table is from a paper I ended up co-writing with some CDC personnel, showing that apart from anything else, the survival rate for these medications isn't great either. It's 23%, which is better than 10%, but still not optimal. And the other thing that we found is that most of these therapies in vitro do not kill amoebas. So for example, fluconazole and sulfadiazine, if you put them in a dish with an amoeba, the amoeba continue about their business unchecked. The other concerning thing is that a lot of these are really toxic. Pentamidine, sulfadiazine, flucytosine in particular, are very, very, very hard for patients to tolerate for any amount of time. So knowing this, and before I'd ever heard of Balamuthia, a collaborator of mine and one of my mentors, Joe DeRisi, had set out on a drug repurposing project. What he'd done is taken a lab culture of Balamuthia and treated cultures with a collection of roughly 2,000 drugs that were approved either by the US FDA or by international countries. The idea is that if a patient came to him and said, I have Balamuthia and I need help, he wanted there to be a drug that you could give this patient off the shelf, not something topical, not something veterinary. He assessed growth inhibition, protection of fetal brain explants, and encystment, that's that tough resistant form. And basically, and fascinatingly, they only found one good candidate. So this graph is looking at percent growth inhibition on the y-axis, significance on the x-axis. You want to be up in this quadrant, but all the typical medications are actually down in this quadrant, so not terribly effective. The exception is pentamidine, but pentamidine is probably the most toxic of the lot and is not really thought to get into the brain very well. So what they found in this promising quadrant were a lot of drugs that are shown in green, which unfortunately are topical, are veterinary, or antiseptics. So bleach, for example, is great at killing Balamuthia, but you can't give that to a patient. In the end, they only found one candidate, and that candidate is called nitroxyline. So what is nitroxyline? It's a quinolone antibiotic. It's been in use for some European countries for urinary tract infections, including Germany, and I am not entirely sure if it is used here, my apologies. It's orally available, it's a pill. It's very, very, very safe because it's been in use for over 50 years. It's thought to act through metachelation, more on that later. And it has pretty nice pharmacokinetics. It gets to a good steady state in patients. But it had never been used to treat amoebic encephalitis. So back to our patient. I did sort of the typical treatments that I've mentioned. I started this patient on 6-drug therapy after talking to the CDC, including pentamidine, sulfadiazine, flucytosine, azithromycin, fluconazole, miltepicine, and also albendazole. An additional antiparasitic was started as well. Unfortunately, this patient ran into toxicities. Pentamidine caused severe low blood sugar and had to be stopped for safety reasons. Sulfadiazine shut down kidneys and had to be stopped. And flucytosine caused severe bone marrow suppression and had to be stopped and then restarted at a much lower level. And on the meds that he could tolerate, his lesions were enlarging, and we thought his prognosis was quite great. And that's when we made the decision to try to get nitroxyline. Now, this is a fairly US-centric way to get a novel medication, but I'd like to talk through it because I think it exemplifies the challenges that clinicians and researchers face. So if day 0 was the day that we said, he's getting worse, we need to get nitroxyline, we requested an emergency investigational new drug authority from the FDA. We went to the patient and said, we don't know if this will work, but we think that it might. Talked it through with him, consented him, got the EIND approved, built a collaboration with Osiris Pharmaceuticals, which is a Chinese manufacturer which makes nitroxyline. They were able to ship it over. That was day 30. On day 32, it arrived, and on day 41, the patient got the first dose. During that time, we kept him on everything else, and it was a time of great anxiety. So I guess the next question is, did it work? Here's an MRI. So in both of these, gray is normal brain matter. In the upper one, abnormal areas are shown in dark black, and this is an abscess in white, and lower ones, bright white is abnormal. This is a pre-nitroxyline scan, and this is post-nitroxyline by 7 weeks. And you can see that it's essentially normalized. We did continue all the other drugs during that time, so I can't say for certain it was nitroxyline, but the timing is certainly suggestive. And the next MRI, 17 weeks after that, looked further improved. The patient has survived, and he is one of the very, very few survivors of this disease. So we thought that was interesting. We put it online as a preprint, and we began getting calls. We were called by physicians who were caring for a child in the Southeast United States who'd been diagnosed by Balamuthia. With assistance from the FDA, the child had been treated with extensive treatment with standard regimen, 2 excisional neurosurgeries, but was having slow growth of residual lesions on all therapy. With help from the CDC and some colleagues in the FDA, we were able to get nitroxyline to this patient. They did better, and this patient is now in remission. Again, we thought that was interesting, but 2 cases is not really full evidence. So we set about doing two things. First, we went back to the bench to understand how nitroxyline worked and learn more about its basic mechanisms. And second, we collaborated with public health authorities to take this work on a greater scale. So I'm going to talk through some of our bench work. Most of this was done by Katie Marquise, who's an incredibly skilled postdoc working in the Derisi lab, and I give her full credit. So first of all, I mentioned that nitroxyline is a metal chelator. That means that we should figure out which metals it works with. So this is a growth assay. This is amoeba growth, and this is different conditions. And this is, you can see that there's no growth on nitroxyline. If you add various substances, it does not grow. But if you give it additional copper and iron, it actually recovers really nicely. This is an iron and copper chelator. The next thing we looked at was encystement. Okay. So I love these pictures. This is what I think of as a happy amoeba. This is a trophozoid, the motile stage, the stage that eats brain cells and other things. And this is the tough resistant cyst. Now, if you give amoebas a stressor, such as galactose, which is one of their environmental stressors, it will form this tough resistant cyst. But when you take galactose away, it'll come back out and become active again. The same is true for hypoxia. But if you give it nitroxyline, it seems not to come out of the cyst form, and it doesn't recrudesce and become active again. So we did some great electron microscopy work. This is over time, looking at controls, and you can see it stays in the sort of happy active trophozoid stage throughout. If you give it galactose, it goes from this sort of trophozoid stage to these beautiful, smooth, resistant cysts. But if you give it nitroxyline, it becomes these sort of irregular, nasty-looking shapes. Some of them look like donuts. Some are sort of vomiting out their contents. They look like they've been stepped on. For someone who likes to kill amoebas, this is very satisfying. But essentially, nitroxyline seems to make it form a cyst, but it aborts halfway through and does not fully complete the process. So we wanted to know what was going on with that. To do that, we wanted transcriptomics. And to do transcriptomics, we needed a genome. Very long story short, the genomes available were insufficient. So Katie Marquise grew up truly industrial grade quantities of amoeba, 100 million amoebas she made for sequencing, and we created and made public a new genome with full 88 chromosomes, fascinatingly much more than humans. That is an entire story in itself, but I'll skip through it and say, once we had the genome, we did transcriptomics, looking at control DMSO versus nitroxyline versus other stressors. Here, red is upregulated genes, blue is downregulated. And what I really want to draw your attention to is basically this column is not like these columns. Nitroxyline institutes a completely different transcriptomic program than other things in stress that stress out amoebas. And it's characterized by an increased expression of genes that are involved in DNA damage and metal binding. The last thing I wanted to know is, are we really killing the amoeba? I am a simple doctor. I want to know that we're killing the pathogen that affects patients. And so I asked Katie to see if we could figure that out. And what we did is we looked at messenger RNA. So this is the activity of a cell in amoebas with different treatments. So in the control, they're producing lots of mRNA. They're happy, they're active. Same if you give them galactose. But if you give them nitroxyline, essentially it goes to essentially zero. This is consistent with death. This implies that they are not only going quiescent into the cyst, but they're being killed. I'll just finish up by saying two other things. One is that after our publication, there was somewhat of a slew of papers that came out looking at the other free-living amoeba, acanthamoeba and Naegleria, and their response to nitroxyline. And basically, they were pretty promising. Nitroxyline really does seem to kill other free-living amoeba species in addition to Balamuthia. At this time, nitroxyline has not been successfully used clinically to treat patients with acanthamoeba or Naegleria, but I will say that I look forward to updating the slide in the near future. And finally, we worked with CDC, and in January 2025, the US CDC launched a nationwide US program to distribute nitroxyline to patients with Balamuthia mandrillaris or other free-living amoebas through expanded access investigational new drug approvals. And a similar process is also in progress in China, which is another nation with a fairly large burden of amoebic encephalitis. To wrap up, Balamuthia is one of the most deadly pathogens in the world. The current medication regimen is limited in its efficacy and severe in its toxicity. Nitroxyline kills in vitro, has a long safety record, and promising clinical data. And we have been so excited to be part of a national public health program that launched in the USA to distribute nitroxyline to patients with this disease. Our goal is to improve the survival of patients with this disease. The last thing I'll say is there are quite a lot of challenges. I did not set out to be a drug repurposing person in any way. So I've been learning on the fly, and I'm very, very, very keen to learn from you all at this conference. The first obstacle here is this is a disease that is terribly rare and is 90% fatal. The standard RCTs are out of the question, and for good reason. In addition, in order to work with this disease, you have to essentially build partnerships with people in CDC, in FDA, like my colleague Dr. Stone here, and you have to work across national boundaries. It's more complicated than your typical academic product. And of course, funding is and continues to be a major issue. There are no specific funding NIH study sections for amoebic encephalitis. This is a real issue for us. So we've tried to get around it with creative assessment of clinical utility, building cross-agency collaborations, and looking at diverse sources of funding. Thank you all so much. This is my email. I'm happy to take questions with my colleagues at the end here.